Welcome back to my YouTube channel. In this video we are going to discuss about the fundamental theorem of arithmetic, the prime factorization method to find the LCM and HCF, and finally the relationship between product of two numbers and product of their LCM and HCF. So first let's see what are the prime numbers. A prime number is a natural number greater than 1 having multiplying factor 1 and the number itself. For example, 2, 3, 5, 7, 11, 83, 89, 97 and so on. So in this type of numbers, if we see 2 into 1, 7 is equal to 7 into 1, 83 is equal to 83 into 1. We cannot get any other prime number except 1 and the number itself in every cases, right? So these are called the prime numbers. 2 is the smallest prime number. Okay. Now let's see what are the composite or non-prime number. A composite number is a natural number greater than 1 and is a product of two or more smaller prime numbers. For example, 4, 6, 8, 9, 200 and so on. Okay. In this case, if we consider 4, 4 is equal to 1 into 4, also 1 into 2 into 2. In case of 9, 1 into 9 or 1 into 3 into 3. Okay. So now if we observe in the factorization of 4, we get two prime numbers. In the factorization of 9, we get another two prime numbers. So these are called the composite number. Also remember the smallest composite number is 4. Okay. Now let us consider any composite number 198. Now we have to factorize 198 to its prime factor. So the first step is to divide the number with the smallest possible divisible prime number. So this is an even number, so we can divide it by 2. We will get 99. Also it is divisible by 3, 33. Next prime number 3 will get 11. So 11 is also a prime number, so we can get any other prime numbers. So we can write 198 in the terms of their factor as 2 into 3 into 3 into 11 or 2 into 3 square into 11. Okay. Let's take another bigger composite number 33660. Now we have to again factorize this. So first step is to divide by 2. To check if the number is divisible by 3 or not, we can check if the summation of the digit of the number is divisible by 3 or not. In case of 8415, 8 plus 4 plus 1 plus 5 is equal to 18, which is divisible by 3. So 8415 is also divisible by 3. So we can write 33660 as 2 square into 3 square into 5 into 11 into 17. Now let's see what is the fundamental theorem of arithmetic. It states that every composite number can be factorized as a product of prime number and the factorization is unique apart from the order in which the prime factor occurs. Now if we observe from the previous example, 198 can be written as 2 into 3 square into 11. Also 33660 can be written as 2 square into 3 square into 5 into 11 into 17. So here we have seen 198 is a composite number and it can be factorized as a product of prime number apart from the order in which the prime factor occurs. That means we can write as 3 square into 2 into 11, which is also correct. Also in 33660 we get prime factorization. This is a factorization, that is multiplication. We can change the order of the prime factor occurring. Now let's see how the prime factorization method is useful to find LCM and HCF of two positive integers. Now let's consider another pair of composite number 26 and 91. 26 can be written as 2 into 13 and 91 can be written as 7 into 13. Now if we observe the power in the prime factor, into it's 1, 13, 1, 7, 1, 13 also 1. Now let's find the LCM of 26 and 91. We have product of greatest power of each prime factor in numbers no matter they are common or not. So from 26 we have 2 to the power 1 into 13 to the power 1, and from 91 we have 7 to the power 1 and 13 to the power 1. As we have already considered a 13 to the power 1, so we don't have to consider it again. Okay, so if we do the calculation we'll have 182. Now let's find ACF of 26 and 91. It says product of smallest power of each common prime factor in the number. And between 26 and 91 we have 13 prime factor is common and the smallest power is 1, so our HCF would be 13 to the power 1, that is 13. Okay, again consider two number 336 and 54. If we factorize this we'll get, so now let's find the HCF. It says product of smallest power in each common prime factor in the numbers. Between 336 and 54 we have 2 in common, 2, and the smallest power is 1, so 2 to the power 1, into also 3 common and the smallest power is 1, so 3 to the power 1, so we have 6. For LCM it says product of greatest power of each prime factor in the number no matter they are common or not. So first we will consider the common factors. Here the common factor is 2, the greatest power is 4, into, again the common factor is 3 and the greatest power is 3, 3 to the power 3 into 7. So the required LCM will be 18144. Okay, now let's see what is the relationship between product of two numbers and the product of their LCM and HCF. Let us consider two numbers 40 and 12. If we factorize this we'll get, now let's calculate the LCM of 40 and 12. First we will have the common factors with highest power into 3 and 5 and we'll get 120. Again for HCF we will have only the common factor with least power, 2 square, that is 4. Now let's multiply the numbers, that is 40 into 12, we will have 480. Now multiply the LCM and HCF of 40 and 12, which is also is equal to 480. So for any two positive integer a and b, a into b is equal to LCM of a and b into HCF of a and b. Okay. In the previous chapter, we evaluated HCF between two positive integers using Euclid's division algorithm, but that method has a limitation. With that method, we can find HCF between only two numbers. But with prime factorization method, we can find HCF as well as LCM of two or more than two numbers. Okay. Let us consider three numbers 12, 15 and 21. If we factorize, we will get. Now let's find the LCM of 12, 15 and 21 is equal to, we'll have 2 square into 3 into 5 into 7, 420. Again, for highest common factor HCF of 12, 15 and 21, we have to consider the only common factors, that is here 3. If we multiply 12, 15 and 21, 3780. Now let's multiply their LCM and HCF, that is 420 into 3. So here we have seen for three numbers the multiplication of the number is not is equal to the multiplication of their LCM and HCF. This condition is only valid for two positive integers. Okay. Now let's take this question. Check whether 6 to the power n can end with the digit 0 for any natural number n. That means in 6 to the power n, if we put n is equal to 1, 2, 3, the result we get, the unit digit is 0 or not. Now see, if we do the prime factorization of 6, we get 2 into 3. Okay, for 6 to the power n, we have 2 into 3 whole to the power n. So if we observe for any number ends with 0, for example 20, 40, 170, these numbers are divisible by prime number 5. So in prime factorization of 6, we don't have 5 as a prime factor. So we can conclude 6 to the power n, we don't get any number which end with digit 0 for any natural number n. Now let's take this question. There is a circular path around a sport field. Sonia takes 18 minutes to run one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So here is a circular field. From this point, Sonia starts to run around the field. She will take 18 minutes. Ravi takes 12 minutes. So a question, if Sonia and Ravi both start to run from the same point in the same direction, after how many minutes will they meet again at the starting point? Okay. In this type of problem, we have to find the LCM of 12 and 18. Okay. So if we write the prime factorization of 12, we get 2 square into 3. For 18, we have 2 into 3 square. Therefore, the LCM will be first the common term with highest power 2 square, then 3 with highest power into 3 square. So answer will be 4 into 9 is equal to 36. So after 36 minutes, both Ravi and Sonia will meet at the starting point. Okay.